So it's recording. Where do I pause it? All right, pause.
Today we're gonna have a new topic called measurement error model, or called a measurement model. We're gonna start from a traditional theory called CTT. Okay, when you talk about measurement, CTT is kind of like a very widely received or very popular theory. And then we're gonna move forward to measurement error model, or just measurement model. And then we're gonna use this model to reinvestigate the correlation and the coefficient. We're gonna see, based on the observed variables, we calculated the regression coefficient B, slope, or the correlation of two variables, rho. Is that truly the correlation or coefficient? So actually there's a phenomenon called attenuation in correlation or regression. So actually those values are, how can I say, not the true value. So there's some noise involved. So we're gonna show the equations for the correct formula, or we're gonna see how there's a attenuation, the correlation R, or the regression coefficient B. And then we will have a lab. Okay, we're gonna do a lot of simulation. So I'm gonna show you how to do a simulation. Of course, how to generate data, and you can design your model and then do the data analysis. Okay, so that's for today's topic, and these are the remaining course schedule. Next Tuesday, please submit all homework. Okay, so homework 5 is due today, but if you have any missing homework, previous homework, or if you want to resubmit your homework, please do that on November 16th. And then we will have a summary of whole SEM1. And so also if you have any question about your homework and the course project, please let me know. And on this day, it's our Q&A session. So the whole session, the whole class is open for you to, for any question about your course project. Today, we're gonna talk about the course project a little bit, the structure of the course project. And of course, homework, assignment, and the course material, and the computer lab. If you have any question about your code, okay, M+ or any other code or email software, just bring your questions. And if that day is not working for you, then we can also make another appointment, okay? And on this day, it's really important, November 30th, basically after 2 weeks, okay? So we have, 3 weeks, okay, starting from today. We will have a course presentation. So each of you needed to do your presentation. So I will send an email for the detailed information. For example, how many minutes? Okay, so what's the format, something like that. And on December 7th, there's no class because it's a Friday class schedule. So we don't have any class on Friday. So we're gonna skip this Tuesday. The last day for this class is December 14th. So your final paper should be submitted before that day, okay? So that's a schedule for the remaining course of this semester. Any question? Okay, good. And for your course project, okay, so at least you should provide 4 parts. And we have presentation 10 points, final paper 40 points. In total, we have 50 points, okay? The first part, introduction. You're gonna tell me what's the background of your project, okay? Why do you want to do this course project? What's the background, and also literature review. So you can just give me some background or literature in your introduction part, but that part is not our focus. That introduction part is not the most important part for our course project. Please do not waste a lot of time in the first part. Second part and the third part is our key parts, okay? And also you're gonna tell me your research questions and your research goal, the project goal. What do you want? to finish the project. Okay. And second part is model or method. That is our focus. So which model? Okay, please describe your specific model. Which model you are going to use? Show me your path diagram, formulas, equations, and also notations. If you have X, Y, or beta, please add the notations. What does that mean? Okay, notations and the rationale. Why do you have that model? Okay, and interpretation. Okay, so you're gonna provide some reasons to support your model. And the third part is also our key part. It's about the data analysis. So in the first step, please show the descriptive statistics, okay, for each variable. So you have your mean, standard deviation or variance or minimum, maximum, something like that. And the data collection procedure. So how did you get your data? Okay, and data plots, okay, and the data analysis procedure. Okay, so if you are using R, then what's the code? Okay, M plus or EQS or AMOS. So how do you do the data analysis? And result tables. Please give the very detailed result tables, estimate and the standard errors and the z value and the p value, something like that. Okay, model fit. Okay, also you're gonna provide a lot of model fit indexes. And the parameter interpretation. You have a lot of parameter estimates. So what's the interpretation? What's the meaning of those numbers? So this is one option for data analysis. If you have your real data, I have another option for you. So you can also do simulation studies. Today, in today's lab, I will give you a very how can I say, it's a very simple introduction of the simulation studies, especially for QM student. You are encouraged to do the simulation studies because in your future, okay, so if you want to do your own research, simulation is very important for you, okay? And please describe your design and the procedure include data generating. So how do you generate your data and the data analysis and how do you do the data analysis? And result tables and also interpretation. Okay. So that's a second option, but for non-quant students, maybe real data analysis is more practical for you. Okay, but for QM students, I just hope, okay, I encourage, but it's not required. It's not required to do the simulation study, but it's very good. It's very good exercise for you. That is the third part. And then finally, we have the first part. What's your conclusion? Okay, what's your finding? And you can also talk about some limitations of your model. Okay, and if you want to extend it, then what's your future research? Okay, so 4 parts. And the second and the third part are our core parts. Okay, so please provide a very detailed information in these 2 parts. And I will give you the grade based on these 2 parts mainly. Okay, of course, and first part and the fourth part is also important, but not as important as the second part and third part. And please also include your references and appendix if you have any. Okay, and please follow the APA style. That is a structure for our course project. For your presentation and also for your final paper, just follow this structure. For presentation, it's the same thing. Okay, so you have 4 parts, and I have some, so I have some points, 2 points for your presentation skills. Please, be confident and talk it loudly and show your gestures, something like that. So for the introduction part, 1 point, because in total for the presentation there are 10 points. Introduction, 1 point. Theoretical model or methods, 3 points. And the part 3, data analysis, 3 points. And the first part, 1 point. And presentation skills are 2 points. Yeah, that's wait a minute, that's not December 7th. It should be 30th. So let me, yeah, so November 30th. So no, November. And December 14th, yeah, that's the final day for submit. So for submitting your paper. So any question? Any question for your question?
For the theoretical, for the method section, do you want us to have a methods section of how we collected the data, the procedures, and all that? Or?
Yeah. So you can tell this part is mainly focused on the theory part, your model part,
Okay.
but not yet the data analysis. It's just your model. And second, the third part is about your data and the data analysis. You're gonna describe your data first.
Right.
The variables, okay, sample size, something like that, describe statistics and the data collection procedures. It's about the data part.
Okay.
But your model part is the second part. So for example, you are going to use mediation or any other model. So why do you want to use that model? What's your model? What's the equation? What's X, what's Y?
Okay.
What's a coefficient? And the residual part, what is the assumption? Variance of the residual part. What's your assumption? So the model part is the second part, the data part and the analysis part is the third part.
Okay.
Yes. Any other question? Good, okay. Okay, then please, it's almost, yeah, finished. We're gonna finish the SEM 1. Next semester, we are going to have the advanced SEM. And it's 3 credit, and that is a CRN number. So the time becomes Monday. Okay, so it's from almost the same time, but it's from 5:20 to 8:05. The same room here. And the format is the same. Okay, basically it's face-to-face, but if you have some other situation, then please let me know. I will have the Zoom for you. So that's information for the second part of SEM, and we are going to cover all of this. Okay, we have the validity, we have reliability. For validity, we have some traditional methods to measure validity, for example, by using the correlations to check the convergent or divergent validity, and also reliability. And then we're gonna move forward to factor models. Okay, factor model is a big chunk of the SEM2. General factor models and also EFE and CFE, exploratory factor analysis and confirmatory factor analysis. And then we can also have higher order factor analysis. Okay, higher order factor models. And we can apply the model to time series factor techniques. And for FA, we needed to identify our model, okay, and how to specify our model. So we have 2 ways to identify our model because it involves the latent variables. If we do not identify something, the solution is not unique. So we needed to do some identification. And then we're gonna talk about the PCA, principal component analysis. We're gonna do the comparison between FA and the PCA. These 2 techniques are quite, how can I say that? A lot of people just treat the PCA as factor analysis. So they use a PCA and they say, okay, I did the factor analysis. No, they are different. Although in some parts they are quite similar, but they are different. Okay, so we're gonna distinguish these 2 statistical techniques. And then we're gonna add the mean part. So far, we just care about the variance part or the covariance part. And we're gonna add the mean and the covariance part together. We have the whole SEM model, structural equation, mean and the covariance model. And we can also look at some very special models, for example, MIFIC model, multiple indicator and multiple cause models. And the model modification. Okay, so sometimes we do have a reasonable, we do have a very good assumption. So we're trying to do the test, okay, some model. But after we run the data analysis, it turns out it's not a good model. How are we going to modify that? We're gonna change the current model a little bit to try to improve the model fit. So we are going to look at the model modification. And also we're going to do the test, okay? Test, some specific tests, okay? Is that 0 or not? Because this is 1 or not? Okay, you can do a lot of tests. And we can also look at the Lagrange multiplier and the word test. And linear growth models. So if we look at the mean trend, so we can see that there's some growth. So sometimes the growth is latent. So we have the latent growth models. And we can also look at the other mean structure models. And if we have multiple groups, we can do multiple group comparison, okay? And also do tests. So between, okay, so among different groups. So are we sure that the coefficients are the same coefficients, the same across different groups or populations or or countries or the same or not? We can do the test. And we can look at the measurement invariance. Okay, so when you design a measure, you want to make sure the measurement is invariant. Okay, so across different population or methods, pencil or computer, you want to make sure that the questionnaire is invariant. So we have some measurement tests, and also we can have the factorial invariance test. Okay, we have different steps. And if we have more time, then we can look at this categorical dependent variable analysis, mainly based on the outcome. Okay, if the outcome is categorical or the dependent variable is categorical, we can do a lot of transformations. For example, the most popular ones are logistic transformation. Okay. Or we can also use a probability transformation. So we have the IRT model. We have a lot of IRT models. But again, this is a very advanced topic. So if you are interested in this topic, you should take the IRT1 and IRT2, okay, from Dr. Kim. So we have 2 semesters course talking about IRT. And also make sure data analysis growth, make sure models, missing data and related dealing methods and the simulation, bootstrap, jackknife, and other simulation methods and other topics for example. But these are very advanced statistical topics. And so if you are interested, then we can just mention that part. It's not our focus on SEM2. So again, as I mentioned, that the factor model is the core of the SEM2. So the goal of factor model is, is trying to investigate the dimensionality of a set of variables or set of items. Based on those items, the questionnaires, tests, we're gonna find out the latent part, the underlying construct, okay? So usually we use construct to show it's a latent variable, undirectly observed variables. Okay, so we're gonna look at the relationship of the underlying latent variables or constructs or factors. Okay, and we can also we can also use some other variables to explain those relationships. Okay, so why do we have this kind of like analysis? So phenomenon. So we can just do the explanation. So the objective of factor analysis is trying to uncover and understand the structure that produces a covert operation in our data. So we have latent structure. We also have observed part, and we're going to look at the underlying structure. Okay. So we're going to involve a very important concept called factor. Okay. This is one example. So we have already used this example in our previous the chapters. We have different measurement and latent variables. So for each latent variables, we have some items to measure it. Okay, and also we have the residual part. So this is just one example. So anyway, this is a preview of the factor analysis. We're gonna look at this again in our SEM2. For SEM1, we mainly focus on the observed variables part. Okay, any question? Any question for the SEM2? Okay. No question, then let's look at today's topic. Measurement error model or measurement models. So far, just so far, we just look at the observed variables part. We didn't look at the latent variable analysis. Now we're gonna move forward to latent variable analysis. Okay, so the very simple case is about measurement error models or measurement models. Okay. And I have already uploaded the chapter 5 to ELC. So if you want to check the details, please go to ELC and look at the chapter 5. Okay, CTT, the famous CTT. Let's start from the CTT. CTT is short for classical test theory. Okay, classical test theory is about test. So in that theory, we assume that the observed y, this y is observed. The observed y is a combination of two parts, two variables. One is a true value, okay? The true value. So this is our real interest. We're trying to measure this variable, but very often we cannot get the true value. So we have some measurement errors combined with the measurement errors. So we have the observed y. So the observed y is a combination of the true value and the measurement error, okay, and our measurement error. And we have assumption for the CTT. So we assume the measurement error has a sum or mean of 0. Okay, it just like the traditional assumption of the error part. And the T and the E, these two parts are independent. Okay, there's no covariance. Okay, among these two variables, there are no correlation, no covariance. It just totally separated into two parts. The true score of y and some noise. Okay, some measurement errors. That's it. This is a classical test theory. But the problem is that we don't know this value. We don't know this value. We just know the observed value. Just like we have observed outcome 5, but we don't know it's a 2 + 3 or 1 + 4. We don't know these two parts. Okay. Okay, so based on CTT, we have very famous concept. It's called reliability. Next semester, we're gonna come back to this topic again. We're gonna show the details of the reliability. We have a series of reliabilities. Alpha, Cronbach alpha or omega or other formula. So we have a lot of like methods or estimation of reliability. But let's try to look at the concept, the definition, okay, the basic definition. So the reliability is actually quantified, it is a quantity to tell us how much of the variance of the observed score is due to the variance of the latent true scores versus measurement errors. So as I mentioned before, we have two parts. Okay, we have the true score part and we have the measurement error part. We want to do some comparison, find a ratio. What's a ratio? The ratio is about the variance part, variance of the true scores and also variance of the observed scores. So in a short way, okay, reliability is about this formula. That's it. This is a variance of the true score, T-score, over the sum of the variance of the true score and the variance of residual part. But remember, we have assumption for CTT. True score and the error part are independent. So the sum is just the variance of the observed variable y. Okay, this is actually the sigma y, sigma square for y. This is a sigma square for the true value. We're trying to figure out these reliabilities. This tells us, okay, how much of the variance of the observed score is due to the variance of the true score. Okay. Yeah, and that's just a definition. And again, next semester, we will introduce a lot of methods to how can I say that? We have a lot of approach. We have CTT approach, or we can have a factor approach, structural measurement, structural equation measurement approach to try to make it very specific. Okay, then let's go back to the error variance. So we have already shown that the sum of the variance, the sum of the the sum of the variance of the true score and the element part is the variance of the y. Okay. So in order to get the top part is variance of the true scores. This is possible way. Okay. The variance of the observed scores and minus this is a sample variance of y. Okay, this is sample based variance of y minus the estimate of the element part. Okay, we don't know this part, the true score we don't know, but because of the CTT, we can. This is easily obtained. It's direct obtained once we have the y observed value, but we can also try to estimate the variance of the error part, measurement the error part. Okay, so the focus is that how to get the variance of the estimate the variance of the error part. But in some cases, we can assume that the sigma e squared, the error variance is known. But in most cases, okay, this part should be estimated. And then I put the question, okay, how are we going to measure the variance of the error part? So actually we have some methods to do that. Look at this solution. One solution is to measure the same construct many times as shown. So our goal, our real interest is in this variable t. And we can try to measure it several times. The first time, we have observed the variable y1. Okay, it's a combination of the true score and the measurement errors obtained from the first time. Of course, we have the variance part. We can also measure the second time. We have observed the score y2. It's a combination of the same t-score but a different measurement error. Okay. And we can also measure the same t by using different units or different instruments. Okay, so sometimes we have different precision. Okay, so different units or different measure with different precisions, we can measure it again. So the same thing, we have the first measure, we have a second measure. So this is another possible way to do that. Now let's have an example to show these methods. Okay, so in this case, okay, the true score t is measured 3 times. Okay, and the first time we have y1, second time we have y2, third time we have y3. And of course, for each time we have different measurement error. These are different, but the true score is the same because we're trying to measure the same thing. Okay, based on CTT. Okay, with that assumption, we have these equations. Y1 is a combination of the same true score and the E1, the measurement at the same time as the first time. Y2 is T, the same T plus E2. Y3 is T plus E3. We can assume, okay, we assume the variance of the true score is fixed. It's sigma square for the T. And we can also assume that these 3 measurement errors have the same sigma square. Okay, so sigma square for EI. Okay, and the independent, the true score and the measurement errors are independent. Okay, T and E, either E1, E2, E3, all of these E's are independent. And among these 2 measurement errors, so okay, E1 and E2 or E1 and E3 or E2 and E3, they are independent. So this is our assumption. Based on the assumption, we can actually answer those questions. What is the variance of the observed y1? What is the variance of observed y2? What is the variance of y3? Covariance between y1, y2, correlation between y1, y2. Okay, so we can do it manually. This is quite a simple algebra. Okay, so we can just do it together. really basic exercise for us. Right, this assumption. By using these assumptions, yeah, we can actually calculate the variance of y1. Because a y1 is a sum of t plus e1. And then we are going to calculate the variance of this part. So it's the same as variance of this part. And just do the expansion. Remember that t and e are independent. Yeah, so basically, if we just expand this part, okay, so we have a variance of t, variance of the E1, and some covariance between them. But because they are independent, so this part is 0, okay? So for the t part, we have sigma t squared. And the variance E part, we have that is the assumption. And for variance of y2, same thing, okay? So it's y2 because y2 is t plus e2. And the variance of y2 is just like a variance of this part. It's variance of t, variance of e2. And we can look at the covariance. Covariance is the same thing, okay? So y1 is t plus sigma, e1, not sigma, just e1. And the y2 is t plus e2. And then just expand it with its covariance. So we have t and t, okay. We're gonna expand this part. This is a covariance between these two. So t is the same, okay. So we have covariance between t and t. It just varies on t, okay, because it's the same value. T is the same. So we have a variance of t. But now let's look at this part. The combination of E and T, they are independent, no covariance. The T and E2, the same thing. E1 and E2, the same thing. E1 and E2 are independent. We assume that the measurement errors at different times or the different measures are independent. There's no covariance between E1 and E2. Then that's it. This is just a sigma T squared. Because we assume that these two are independent, and also these two are independent, and these two are independent. Okay. Yeah, so all of these are independent. So we don't have the covariance part. We only have the variance part. Now let's look at the correlation. Correlation, what's the formula? It's covariance between y1, y2, square root. Variance of y1, variance of y2. We have all these components ready. So we have sigma t squared. That is the variance between y1 and y2. We have the variance of y1. Okay. And we have the this is the variance of y1 and y2. Just follow the formulas. So it's quite easy for us to get the formula here, okay? In this case, it's exactly the same case, but here we use different notation because in SEM, we use a C and eta. Okay, so it's different. I'm sorry, this is different. So in this case, the observed value y is here, and the true value of x is, see here, the true value of y is eta here. So based on the CTT, this is the true value of x, this is the true value of y. So the combination of this one and the E1 is observed x. The combination of the true value eta and the E2 is the observed y. So just follow the same structure. Just follow the same calculation. Okay, we have the CTT for both x and y, variance of t, variance of e, assumption of t and e, assumption of E1 and E2. Okay, so we have the similar questions. I'm sure it's the calculations just like the previous slides. We only needed to do the combination of y1, y2, y3 here. So here we have x and y, and follow the same, follow almost the same notation. Notations are different because here we have two different variables. Because now we are trying to investigate the correlation between two variables, x and y. They are different. So we have we can just modify it, okay, for x, because now we have the c here. For y, we have eta here. So we have eta here. And for colors, okay, this is different because we have c here and the eta here. X here, y here. So the t is not this value. It is a variance of, it is covariance between C and E. Okay. And the rest part is independent correlation. So we have, here we have x, y. X, y. So that is we can assume this is a covariance between C and eta. This is a covariance between C and eta. So this part is C, this is eta. That's it. Yeah, we just change the notation. Because now we assume that x and y are different measures for different variables. In the previous case, we have the same t. So the derivation of these components are the same. Yeah, and also we can let's look at this path, but not that path diagram. Yeah, it is also you can also regard treat this as a path diagram because we have the circles and the squares. So we just calculate the correlation. Okay, here we just calculate the correlation between x and y is a covariance between x and y here. Okay, so here this formula is the same as this formula. Okay, so the covariance between c and y, the covariance between these two values. This is a variance of x. Okay, this is a variance of x here, sigma 1 square. Okay, the same sigma E1 square. This is a variance of the y. This is a variance of x. So this formula is just this formula. That is a correlation between the observed x and the observed y. But actually, we are really interested in this part. Okay, the true correlation between C and eta, because this is a true score of x. This is a true score of y. So this is observed x and y part. Yeah, question.
So for xi always represents the variance of x, correct?
You mean this See?
Yes.
Yeah, so this is a true value of the x. Because,
And,
yeah,
and eta always represents the
true value of the y.
y. Okay.
Yeah, yes. So if you do the comparison, this correlation, okay, this is the correlation between the true value of these two variables. This is the correlation between the observed x and y. You can see these are different. Yeah, if you do the comparison, the top one is a true correlation. That is a true correlation. That is a correlation between these two values. So we have the covariance between c and eta. We have the standard error. Okay, or you can think about the variance, square root of the variance of the c square root of variance of the eta. That is a true correlation. This is observed correlation. If you do the comparison between these two correlations, they're different. With the top one is a correlation between c and eta. They can the two scores. The bottom one, the row xy, is a correlation between the observed or manifest variables x and y. This is a relationship between them. Yeah, because yeah, let's check the bottom part. Let's check the bottom. If you do the comparison, the top part is exactly the same. Okay, the top part. But if you check the bottom part, here, in addition to this part, we also have some noise involved. This is due to the measurement error of the observed x. In addition to the two variables, we also have the sigma square for the second measurement error involved, because this is due to this part. So if you do the comparison between the bottom part of these two equations, the bottom part, this is larger, but because it's a ratio in the bottom part, so this value is actually larger. This value is actually smaller because we have some noise. These are noise. We don't want to get that, but it's avoided because it's in the real life we have to consider the measurement error. So we have some sigma 1 squared and sigma 2 squared. But if you do the comparison, this one is higher, this one is smaller. So the true correlation between two variables is larger than the correlation between these two observed variables. So what do we observe as a correlation actually smaller than the true correlation based on the CTT. So that is called attenuation of the correlation. This phenomenon is called attenuation in correlation because what we observed is smaller than the true value. And then people trying to propose to correct that one. So these slides is from my other course, regression course. I also teach the regression course. So in that course, we have formula to show the correction for attenuation of correlation. But in that course, I just give you the formula here. I didn't tell you why, because the logic, okay, so the reason is here. The reason is here. We have to involve the measurement error part so that we know why. And this is a true, this is a correct version of the correlation between variable 1 and 2. This is observed correlation. And what are these? These are actually reliability. So this is actually defined in these slides, reliability. So by looking at by obtaining the covariance of the observed correlation between x1 and x2, and also the reliability of x1, reliability of x2, we can actually have the correct formula, the corrected version of the correlation. Yeah, so in that course, we said, okay, I said that in behavioral research, variables are not measured without error. So we cannot perfectly measure those items. We do have some measurement errors. So because of those measurement errors, so the correlation actually we obtained is dampened by the actual noise associated with the measurement errors. Okay. And in order to correct those noise, and we have a correction for attenuation. Okay. So that's a formula. That's a formula. But why have this formula? Why do we have this formula? Actually, we can totally derive it based on this formula. Okay. So we have already obtained this formula, or this formula is exactly the same, but it's the same thing. Okay. And this is what we observed. We're trying to get the correct correlation here. That is the correct. So it's so messy. Let me erase all of that. Okay. Now we can just look at this. We're trying to get this formula starting from this formula. So this is observed correlation. We're trying to get the correct correlation. That is our goal, starting from here to get here. So what's the translation? That is a formula. Okay, so let me just show you how you get that formula. And actually the exercise is very good because in your own research, you can have some other, you can have your own formula to correct some observed statistics. Okay, so you can think that, okay, some formulas are not quite accurate. So we can have an improved version or correct version. Just like we did here, just wait, we are going to here. We're going to do here. So we have the formula here. And we're trying to start from this formula to have that formula. So just do the comparison between these two bottom parts. Let's do the comparison between this one and that one. Okay, so starting from here, because the final goal is to get this term, but we need to do some transformation. Okay, so we can have this transformation. We will move this part a little bit further. If we have this term multiplied by this original term, we cancel these two parts. Okay, we cancel this part, this part, this part, this part, and then we have a new bottom here. Then the formula is exactly the same here. So we need to time this term based on the previous original observed correlation. So what is this term? What is this term? Let's take the square root out. Okay, so if we use the square root like this, okay? So the one square root. That's the same thing, but when you check this part, or when you check this part, what is that? This is just the reciprocal of the reliability of X. So think about the reliability. Okay, for X, it's a sigma of square. Okay, this is a true score of X over the true score plus the residual, the variance of the error part. This is the reliability. You can use the reliability of X, okay, for X prime. Reliability of the X and the X prime actually is the correlation between these two. Okay, it is this definition. We just define the reliability is this formula. So let's compare this term and this term. It's just a reciprocal of the reliability. So that's why we have the original observed correlation between X, Y divided by, this is multiplication, but if it's a reciprocal, it's the same thing. Divided by the reliability of X to square root. Same thing. What is this term? What is this term? This is a variance of eta plus the variance of the error part. This is a variance of eta. Think about the reliability of the Y. Okay, it's a variance of the true score over the variance of the true score plus the variance of the measurement error. So here, the same thing. This term and this term is just a reciprocal. So we're gonna divide by the reliability of Y. Of course, we have the square root. And then after do this transformation, we have this term. What is this term? This is a true correlation between these two variables. We focus on the true value. So this is observed correlation. This is the true correlation. Okay. So by using this formula, the observed correlation divided by the square root of the reliability of X and the reliability of Y is the correct version. So that's why we have this formula. Okay, R12 is just a correlation between the observed X1, X2. So here we use XY, the same thing. Here, the X1 and X2. This is the reliability of the first variable. This is the reliability of the second variable. By using this formula, we have the correct correlation. Okay, observe the correlation, true correlation, true correlation here. So that's why we have this formula. This formula. That's why we have this formula. Updated version of the correlation, or the corrected version of the correlation. So the underlying logic is based on the measurement error model. We need to make sure that the observed value has two components, the true value and the measurement error. So we have some reliability concept, and also we have attenuation for correlation, and then we have this corrected version. Sorry, is that too tedious? Did I explain it clearly? Yeah, okay, sorry, yeah. Any question about this part? So we just show that how to correct the traditional correlation. Same thing for regression. We have independent variable X, we have dependent variable Y, we have the intercept A, we have the coefficient B. The B is also not the true B, it's observed correlation slope. The same thing, just like the correlation. So we have the observed X, we have the observed Y. We are actually really interested in the true value of X, which is C, and the true value of Y, eta. We trying to get the beta. Beta is a true correlation. But because we cannot measure X and Y perfectly, we have some observed correlation B. B actually is a, how can I say, it's a practical version of the true correlation beta. We're trying to get the beta. Okay. So this is an observed version of the regression, but actually this is a true version. So there's a version of the true regression variables, okay, latent variables. So the beta here, okay, so we have the C is a true value of X and the eta is a true value of Y. And then we have the beta here. Wait. Same thing, we gonna have an updated version for the observed B. Okay. So here, we just follow the traditional definition. The regression coefficient B is estimated by, okay, the ratio of covariance between X and Y over the variance of X. And the covariance between X and Y, just like before, we can just derive it based on the CTT. Sigma C eta is the covariance between X and Y. Okay, just like we did that. That's what just like the slides here. Yeah, the slides here. We derived the covariance between X and Y. And also variance of X. Variance of X is the variance of the true score of X plus the variance of the measurement error. But the true score version is just described here. Okay, the covariance between C and eta. The top part is the same. It's a sigma between eta and C. So this is the variance part. But we needed to use the variance of the true value of X, which is sigma square for the C. Again, if you do the comparison between these two, this is observed coefficient. This is a true coefficient. The top part is the same, but the bottom part here, we have some noise, okay? So by doing the comparison, the observed coefficient is smaller than the true coefficient, true slope. Imagine there's a, I'm sorry, yeah, excuse me. So imagine there's an ideal world, there's no measurement error. In that case, the coefficient is larger than the coefficient we obtain in this world, okay? So this is called attenuation in regression. What we calculated, what we observed is not the true slope. It's a smaller version of the true regression coefficient slope, yeah. And of course, how to correct that? The same logic. You can do it by yourself. It's really simple, just like the previous formula we did for the correlation. Starting from the observed coefficient slope, okay, we can have the true version of the slope. It's above the reliability. Okay, if you do the comparison, this part is just reliability of X part. Okay, so the B divided by the square root of the reliability of X is the correct version of the regression, the true regression slope. Yeah, so I can leave this question to you for your exercise, okay? Because it's really simple, just do the similar exercise. Any question? Any question so far? So everything, all of these formulas are derived from, yeah, this formula, this path diagram, or this assumption, or yeah, just this CTT, the classical test theory model. Because what we observed is not the true score. Okay, we don't get the perfect score. So that's why we have two versions. We have different versions. So that is kind of like a, yeah, summary or remarks. So results based on the observed data are attenuated. So you can do the comparison. The observed values is smaller than the true value. Okay. if errors are known, then attenuation can be corrected. Of course, if we know that, we can just directly apply the formula to get the correct version. Inference based on the latent variables is preferred because that's our the real goal. Okay, real interest to get those latent variables, true latent variables. And to estimate the latent variables, more than one observed variables are needed because we're trying to get the measurement areas estimate. Okay, so I think I already finished the theoretic part, and the next session we will have the lab. Okay. So we can do the exercise for different examples. Any question? Any question for the measurement error part? Question? Yeah.
Can you like give us an example, like in the data set, what is the observed value, what is the true value?
For example, you want to test the students' math ability, but you don't know the student's math ability. You have to use some tests to get the score, but actually the score is not the true value of the student's math ability. It just, okay, the student's ability plus some measurement errors. The measurement errors coming from the, for example, your questionnaire, your design of your questions, or your format. Is that computer version, or is that the paper pencil version, or your instruction? So there are some other factors gonna influence the students' observed math score. But actually the math score is just observed mathematical ability. It's not the true value. Yeah, so we have some students, of course, if the students have a really high math ability, he or she can have a very high score. So the observed score Y is influenced by the true value, but it also influenced by other factors which are measurement error. It's due to your measure, okay, it's due to your measurement. If you're trying to get the true score, you have to use some tools to measure it, but you cannot get the true score without any measurement errors.
So
Yeah.
the observed value are like the respondents.
Yeah.
Like that is you collect in the data set. But
Yes.
the true value, you have to consider the measurement error to get the true value. That cannot be directly obtained from the data set.
Yeah, you can think about that way. So the observed math score, the student math score, is partially influenced by the student's true score and also some other factors. Yeah, so that's one way to measure the student's math ability, but it's not perfect. We have some measurement errors. Yeah. Okay, good question. Yeah. Any other question? Okay, then let's have a break, and we can have a lab. We will have a lab in the second session. Okay. Yeah. Question. Yeah.
So are you gonna go into detail about the project next week?
Detail the project. If you have your own topic, just bring your topic to me,
Okay.
and we can discuss. Okay, what's your plan? What kind of research question you have? Then we can design a model. Yeah.
Okay.
But in general, that's it. That's a general, your structure of your course project.
I have one more question.
Yes. Yes.
I guess for number 2, you said you want us to show formulas and equations.
Yes. Yes. For example, if you want to use mediation, then you should have your equations. Okay. Yeah. Just like a.
On the slides.
Yeah, the slides when we talk about mediation or regression or moderation.
Okay.
Or yeah, you should have some formulas or equations for that model.
Okay.
Or just that is a mathematical version of the path diagram. You have the path diagram. You also have the math equations. So these two should be equivalent. So these are kind of like 2 ways to show your model.
Okay.
Yeah.
Okay, I asked my questions and then please say it anyway.
Okay.
Thank you.
Yeah. Okay. Okay, then we can have a break. Okay, for 15 minutes. Yeah, we're gonna continue our next session on 7 o'clock.
So that we have like a whole class day.
Do you have idea that you want?
Kind of, but I don't know my data set really fits what we need to do. I have a data set for my job, but it's not item level data. It's it's at the contract, like raw score.
Right.
Deeply encourage the
What about you?
Yeah, but I have multiple
Did it really just-
mediators.
Mhm.
So I don't know
I'll
how
have to
you
think about that. I was just gonna say
equate both
something.
versus
I think she's
the
doing
second media set.
simulation today or something.
I guess that's one thing.
I think she's
Well, that's the
doing
way I would do it. I should sit down and talk.
I mean, technically,
Yeah,
don't have that day
that's what I
off,
have to
but
do.
that sounds like we don't.
Right.
So if we
You
use
are-
our own data, we would need data.
I don't know.
at item level
Are you going
It's
back
something like-
home?
To be able to do
No, I'm
really
not going.
structured
My
quick tomorrow, and I'll tell you the
Oh,
example
good.
from my
So-
workplace, we
but-
have.
You are talking about IRT actually. Yeah, from
So
the
I do have
response.
IRT data.
Yeah.
So that's one
And
thing. So I
then-
have one skill that's an IRT
Using
skill.
it like-
Okay.
it's like a
Um,
baby
but all
SEM.
I
It's not
get
even
back from
SEM.
that, from,
Predictive
it's all from a
one.
vendor, it's
Okay.
STEM score, so I don't actually
And
get
then
raw
With how many
scores at the
variables, how
item
many
level.
Uh-huh.
And then same thing, I have personality data
Yeah.
from the
Or independent
Hogan, I don't know
variables
if you've ever heard of that, it's
It's
like a
like
very
four
popular
sources.
commercial
Uh-huh.
measure of personality.
Uh-huh.
But again, I have raw
Anyways, the fourth thing's
scores at
predicting one
the
thing.
dementia level.
And then I
Okay.
was
So
gonna
like
do
the
test for
factors, I have the
factor
scores on, but I don't have
factor
item level scores.
by gender, 'cause it's an engineering.
So it'd really be
It's
more
like
like a
engineering
path analysis.
So you could
than
do like
wouldn't it,
moderation.
than a
Yeah,
true
I
structure
think
equation.
you can just
It's
choose
class.
some
Right,
items
you might
for
do
this,
something
just do
like
the project,
Yeah.
because if you use
My
all
struggle,
items,
though,
definitely you're
is-
gonna expect the models
I have
IRT
so
models,
many
which is
items
more
for those
accurate,
four,
more,
like predictors.
yeah, so, for
And like I
the,
have to.
this is the
do
first
if I
class
just
of
like
math,
even
yeah, so
tease
for
them
this
out, 'cause
class,
I
it's
know
very
that some
basic,
items
so
are
you
gonna
can
go
just
out, but
choose a
like for the
subset
library,
of the
I
original four data sets, do the analysis, and then the next semester.
I think what
you can
makes me
use
so
all the
nervous
items
is
and
like
just do the full
rotating
SEM.
factor.
Okay,
Yeah.
Yeah.
but like for those, so say like
Yeah.
a scale of like
Do you have
extroversion,
SES?
all I have is like, you
I
know,
have
this
it.
person
Yeah.
scored a 26 on
Um,
extroversion. I don't have like at the
I also
item
have it
level,
plus.
like they answered
I
this
see.
item
Okay.
this way.
But
I'm just
Yeah,
thinking
yeah,
about
yeah.
what Dr. Kim did.
Just
I think
use
we
it.
only use.
Make it
He
up.
used every freaking
That's right. I
Available.
remember how to sort it
Okay,
by.
and I will,
just
I
print
plan to
out.
schedule some office time,
Okay,
to just
sure.
kind of talk to you
Yeah,
about
so
my
I'll
data,
look
because
at
it's the
that.
data I want to use for my dissertation
Okay.
anyhow.
Yeah.
So I'd be
Because
interested in
rating is
your
mostly
input.
decision.
Dr. Khan is
You look at
my
how it is.
methodologist. I know you work with
Oh.
him.
And
Oh,
you would
yeah.
With Jill.
know.
Okay,
how
sure,
you're
sure,
gonna
sure, yeah,
use
yeah,
the
yeah,
data.
yeah,
So,
yeah,
You
yeah.
have clear
I've been
Oh,
Clusters
clusters
also,
that
you,
are
okay, Jill is also your.
right angles to each other, then you do
She
like
is.
box
Oh,
scores.
So
yeah,
Dr.
she's
Watkins
excellent.
is
But if
my
they're kinda like-
advisor.
Oh,
and
I
Dr.
see.
Klein's my
Angles, then you would
methodologist.
use
I see,
that.
both of them are excellent,
Right.
yeah,
Yeah.
three of them are excellent.
They say the same thing about you, you know, they're
Yeah,
like,
I
oh,
just
you
love
know,
that.
take it. All right,
Why?
awesome.
Okay, good.
Just so I can see if I can run the thing and then see. And maybe you look over. Yeah,
So
figure out, yeah, I think that's my trouble. That's probably why I'm gonna come to that class in case I don't like, still have no idea what I'm doing, which I should. This project's also been done before, so I do have notes of like, it's like someone who was more senior to me. She started the project and never finished it.
Hmm.
So like, she picked it up. I have like a whole document of like what she found. So I'm like, can I get the same thing?
mhm.
Or at least something close, because I don't know what her data was like whenever she did it, so. But I also have data if you want to use data.
I have some too, but I'll probably do this one.
I don't even know if that means, to be quite honest.
Just make up data.
Yeah, I guess I get that. But like, what is a research question even like?
So like my thesis was a simulation study, a big one, and it was all to test whether a model works. So you create data where you know the true value.
Like it should work.
Well, not that it
Well,
should
if
work,
it
but
doesn't-
you know if it doesn't, because you know it's real. It's like
Right.
here, like the example that Dr. Lee just gave, you don't know people's true math ability in the real world. But in a simulation, you
You
do,
can like
'cause you make
fake
it up.
it.
Yeah. And then you use your model to see how well it does estimate.
It will probably be similar.
So like with
Yeah.
simulation, you're really more testing like methods. The model that you choose.
Yeah.
No. But it seems fun. I mean, it seems really interesting. Like have your
Yeah.
mind.
Yeah, I haven't thought about simulations this class, so kind of model it and look at it, because I'm going to try to relate it to my stuff.
Yeah.
Like the models I work with.
That's my issue.
I
It's
should
like
learn to see how it relates.
I have another
think of
question.
Yeah, yeah, sure, yeah, yeah.
Okay, so for example, pertaining to
Like it
part
is,
2,
yeah.
if we have more than one mediator,
Okay,
do we need to show
Still an estimate.
more than
Still
one
a step up
mediator
from that.
equation,
Yeah.
or?
you're right. In that case, it's more complex than the traditional way.
Mhm.
Yeah. So what's your, do you have a path diagram? Yeah.
I could. put
Yeah.
my name.
The first step, okay, always show your path diagram.
Okay.
Based on that, we're going to have some simulation studies, okay. We have two examples. The first example, use one observed variable, okay, just one, just single variable y. Of course, the y is a combination of two parts, true value and as a residual, as a measurement error part. And we assume, okay, this is the true values of the measurement error here. We because it's simulation. The first step, you have to generate your data. There's nothing there. So simulation, you have to generate it. How do you generate the data? You have to use some assumption. For example, we assume the true value is coming from normal distribution with mean of mean of zero and variance of 1. We're gonna also assume the measurement error part is coming from a normal distribution with mean of 0 and the variance of 0.25. That's our assumption. So based on these assumptions, we generate our data. I will show you how to generate data in R. Based on the so after we generate data, we save the data somewhere, okay? And then we pretend that we only know the observed data. And we have some analysis model trying to estimate the true value. So 2 steps for simulation. For real data, if you have your own real data, you're gonna skip the first step. You don't need to generate your data because the data is already available for you to do the data analysis. So you have your own model and trying to use your model to explain your data. But for generation, you have 2 steps. The first step, you generate your data and then you analyze your data. You're gonna also compare the estimate of the parameters and the true value to see if there's a big difference or if there's a very close to the true value. That's for simulation. And the simulation for these 2 examples. The second example, we are going to use 2 measures, y1 and y2. Okay, we have some other part. So let's look at the first example, one variable. Based on the CTT, okay, this one variable y is sum of this true and the e. And in the population, what does that mean? The true world is, okay, the true part of this data is the t, the true value is coming from normal distribution, mean here, variance here. The e part is coming from a normal distribution, mean here, variance here. And first, let me ask you the same questions we did before. For single variable case, how many observed variables? How many observed variables in this case? Just one. What is the number of information? When p equals 1, the formula is p times p plus 1 divided by 2. What is the number of information in this case? What is the number? What?
Is it 3? Oh. 1.
Yes. 1. That is okay. This is 1. For one variable, the number of information is 1 because the formula is p times p plus 1 divided by 2. 1 times 2 divided by 2, it's 1. What does that mean? We can only estimate one parameter. We cannot estimate two parameters in this case. Okay, so we can estimate at the most one parameter. If we have one parameter, the degrees of freedom just 0. You cannot estimate 2 or 3 or other number of parameters. So it is this case. Then let me show you the code, okay? Of course, the first part is this part, okay? This part is from here to here. This part is a data generation, okay? We generate the data by using this code. Setting working directly. I don't want to mention it anymore. Okay, set seed. Okay, set dot seed. Why? The seed is for random variable. In the next two rows, we have R known. R known. What is the meaning of R known? R known that I'm gonna generate a random. R is short for random. Random variable from normal distribution. R known. Random variable from normal distribution. And then R norm is a function. Inside the function, we have to tell R what is your sample size, how many random variables you are going to, how many random values you are going to generate. In this case, 1000. Mean, the second parameter, the second position. This is set error in R. You have to tell the R code, okay. What is the set error of the normal distribution? So in the previous case, we have this is the variance, okay, so in this part, it's a sigma squared. So square root of the sigma squared is a standard error. So this is the square root of the variance part. This is the standard error, because in R we use standard error version, not the variance version. So R norm is just random. Every time you generate these numbers, it's different because it's random. But in order to keep the generated value the same, you have to set a seed. Okay, if you fix the seed, okay, set dot seed. If you use a seed number, that number is today's date, okay, 2021, November 9th. If you use the same seed, all the students will have the same generated value. Otherwise, if you ignore the seed or if you use different number, the data generated by him is different with the data generated by you, and it's different. So we have 20 students here. We have 20 versions of the generated data. That's still okay. But if you want to do the test, for example, later on, we're gonna check the bias. If you want to make sure each student have the same result, we can use the same seed. If this seed is same, all the students have exactly the same generated data. So that's the purpose of the seed. Of course, you can just ignore this seed line. It's totally fine. But you will have different set of generated value. Again, all of the data are from normal, but because it's random, it's some different values. Okay, just like a sample, we have different sets of sample. Okay, and the T true score coming from normal distribution. That one. Okay, Y. Let's look at this Y. Y is a sum of these two parts. Sum of the previous T add the measurement error. This is the measurement error. Okay, T plus E, we have observed Y. And you can use write table. So previously we talked about read dot table. Read dot table is that read the outside file into R. Now we generated the data in R. We want to save the current data set. Then we use a write dot table. Write the current table Y to an outside, okay, the file name is here, error m plus data. So of course you can name it error R data, it's up to you. This is the name of the generated data, which is saved to your local folder, to your working directory. So you have your own working directory. The data file will automatically saved to your folder, to that folder. And row name, column name, so those is true, false, you can just make it the false. No row names or column names. That is data generation. We have already done that just by using R node. Of course, if you want to generate the random values from T distribution, then you can just use RT. Or random values from T distribution. Okay, so you can change the distribution here. You can change it to chi-square or other functions. Okay, but you have to check the function because you also need to input your degrees freedom for T. With different degrees freedom of T or chi-square, the distribution will be different. For normal, you have to make sure you're gonna provide the mean part and the standard error part. Okay, this is the mean part, this is standard error part. So that's it. We have generated the T, we have generated E, combine this T and E with a Y. And this Y is saved to this data set, okay? The next part, we can, from here to here, we trying to use a SEM model to do the estimation. So this is a variance of Y, okay? So variance of Y. And also making it as matrix format. This is a format. And we are going to use the SEM package to do the data analysis. Data analysis of this SEM package, okay, SEM model. Specify model, here, let's look at this case. T, okay, T goes to Y, NA, 1. What does that mean? T goes to Y, and NA, 1. What does that mean?
Starting.
Really?
We're fixing it to 1.
Yes, exactly. Yeah. So I don't need to estimate this coefficient from T to 1, from T to Y. It's fixed. This coefficient based on the CTT. This is fixed. This is not a parameter in CTT. CTT is Y equals T plus E. The coefficient are always 1. Coefficient, this coefficient and this coefficient is fixed at 1. There's no beta here, not just regression. It's not a regression. So this part is fixed. So the coefficient from T to Y, no need to do any estimation, NA. And the value is fixed at 1. It's fixed at 1. And then let's look at this part. What does this mean? Okay, T goes to T and the double-headed S1 NA. What does that mean? This part, what does that mean?
Estimated
Estimate of what?
S1.
S1, what is S1?
Variance.
Yeah, so I name it S1. Actually, it should be sigma T squared. I want to know the true variance, the variance of T, the variance of the true value of T, starting value NA. So, but anyway, I want to estimate the variance of the T value, true value. And then what is this? Y goes to Y, NA, dot 2.25. What does this mean? Variance of the residual of the Y, which is sigma E squared, NA. I don't want to estimate. And this one is fixed at 2.5. This is variance, okay, variance of residual Y, variance of residual Y, fixed at this value. Then some people may ask, okay, why do we want to estimate that one? Because we don't know this part. We want to estimate. We can estimate this one and also this one. Why this is not allowed? Why? Why we cannot estimate the sigma T squared and the sigma E squared? Exactly. You cannot estimate this and this because in that case, you're gonna estimate 2 parameters. But for the case of one variable, you have one piece of information. That's it. You at the most you estimate one parameter. You have to fix somewhere. You have to fix here and to estimate the sigma t squared, or you fix this part to estimate this part. You cannot estimate both. That's not allowed. Thank you. Yeah. So in this case, we assume that, okay, this part, I assume this part is known. This is the true value, okay? The variance of the residual of the one is 0.25. Then we're gonna estimate the variance of the true value. True value. So this is our model. This is our model. This is our covariance matrix. Covariance matrix. This is our sample size by using the SEM function in the SEM package. We have the estimated result. You can check the summary result. Okay. So that's our code. Let's just do it together. Please download the R code from our ELC. Okay, so go to ELC. Here we have R file measurement error. Actually, I also provided these two, but text file. But the text file is not required because you're gonna generate the text file by yourself. So you don't need to type the text file of these two, because by using the R code, you will automatically generate these two data sets. Okay. Okay, so please go to RStudio. Yeah, so when you are ready, you're gonna set working directly. Okay, of course, you can manually set it by input this path, or you can just go to session, set working directly, choose directly, and choose your own folder. And the library, yeah, so library SEM text the package here. And that is an example of first example. So actually the code is different. It's a little bit different as the version in the slides here. We generated T by using this function. We generated E by using this function and add them together. But actually the final result is exactly the same. In the code, in the slides code, we have Y equals T directly add this part. Okay. Here, I just want to make sure that this part we have T ready. This part we have E ready. And after we add these two parts, we have Y ready. Okay. So we're gonna set C and generate the T. And if you run, you can just check T here. Okay. If you type T here, so you have the 1,000 random value ready for you to use. Okay, those are from normal distribution. And you can also highlight this part for E. If you want to check the histogram of the T, okay, yeah, that's it. You can use hist, okay, histogram here in the console part. I tried to type in the history T. And that is a description of the T value. So it's quite normal, okay? The mean part is 0, okay? This is 0. And the standard deviation is 1, okay? So here we have 2 standard deviations, almost all of this covered. Okay, so that is a histogram of our T, the true score. And you can have this. And E is the same thing. You're gonna generate the E from normal distribution with zero, with mean of 0, and the standard error is square root of the variance, because 0.25 is a variance, sigma squared. Okay, if you want to look at the sigma, just take a square root and highlight this part. You can also check the histogram of E. Okay, so let's look at the histogram of E. Yeah, so here, so this is the E part. Yeah. Actually, it's a smaller, actually, because here the notation, look at the scale, it's smaller than the previous T, because here we have the variance 0.25. And then add these two together, y equals T plus E. Of course, y is normally distributed, so you can also check the y part. For example, you want to check y, the lowercase y in my case. Okay, so if you use capital Y, it's not recognized. Okay, so you can. So it's a combination of the T and the E together. Okay. Now we're gonna save the Y. Okay, the Y is ready. So if you type Y here, or you can just check the Y here. These are Y, 1,000 of Y values. It's a combination of true value and the error part. If you want to save the data set, then use write table, write.table, the Y and the name of your file. It's called, yeah, you can just change those. You can just change the name of the file. And that's it. After you run this part, automatically the local folder will have the data ready. This is new data set. It just generated at 7:27 p.m. It just now, okay, 7:27 p.m. It's a new table set, the table data file. Yeah, you can just check the Y variable. Done. Okay, the first step done. Data generation done. And we are going to use SEM package to analyze the data. We can calculate the variance of the Y variance matrix. Variance, this because there's only one variable, so the variance actually is scale. And we try to make it a format as a matrix because we are going to use the SEM function. Okay. You can also name the columns and the rows as Y, but it's optional. It's not very important. Yeah. So the variance, check the variance part. The sample variance is 1.25. It actually is a variance of the true score plus a variance of the residual part. Okay, 1.27. It's very close to the true value. Okay, this is a sample version, 1.27. And we have the model here. So this is our model. The coefficient from T to Y is fixed at 1. The variance of true score is S1. We are going to estimate that one. We are going to estimate the variance of the true score. And the residual variance is fixed at 2.25. Okay, highlight this part. And trying to run the model. Okay, trying to run the model. Let's check the model. Model result. Okay, model result. So this is a simple result. If we just type in the model one estimate, this is summary result. It's more have more information. So we're gonna check summary result here. We just estimate one parameter. Okay. Oh, this is, we can just run it again. Make it 1, 1. Yeah, this is better. So just look at the result here. We only have one parameter estimated. S1, the variance of t, true score, estimated as 1.02. What is the true score for variance of t? What is the true score? When we generated the variance of t, when we generated the t-score, what is the value? Variance of t? 1. Now we estimate it as 1.02. If you want to report the result, you're gonna estimate it, you're gonna report as a bias, okay? This value minus the true value, 1.02 minus 1. So the absolute value of bias of this estimate is 0.02, which is really good. This is the standard error of the estimate, okay? Standard error of the estimate. Z value of this estimate, the probability, okay? So you can also report the relative bias, okay? So you have the absolute bias, okay, the estimated value minus the true score over the true score, you have the relative bias. But in most cases, the absolute bias is enough. So the estimated value will be reported, should be reported, and also some comparison. Also, you can compare you can also report the estimated square plus the standard error square, so the variance part plus the estimated square. So it's called the MSE, okay, MSE. It's another statistic to measure if the estimate is recovered well or not. Here, it's pretty good. Actually, it's pretty good. And I'm sure that each of you have the exact same estimate. Now let's try to delete the seed. Okay, so go back to the code. Go back to the code. I'm gonna put a comment here. In this case, I didn't set any seed. Okay, so I'm gonna rerun everything here. So without the seed, I'm gonna do it again. I can also make it 100. Okay, make the sample size small. For example, 100 is also good. Okay, 100 without the seed, and make it 100. So let me try to rerun this part. And various part. The same model. Okay, I didn't change the model. Now let's look at the estimate. The variance of the true value is 0.8. It's 0.8 for my version, but if you use your own code, it might be different because we have different seed. Okay, we have just random variables. So some of you might close to 1, some of you might, okay, for example, to have 0.9 or 0.95, something like that. It's all possible. But if you fix the seed, then all of us will have exactly the same result. That's a function, that's a goal of seed. Use a previous version. And in this case, because the sample size is smaller than the previous one, so look at the estimate, the bias is larger. Okay, so 0.8, the true value is 1. When we generate the data, the true value is 1. But what we estimated, the value is 0.8. So there's a 0.2 bias. The estimate bias is 0.2. Okay, that of course is absolute bias. And the standard error is also larger than the previous version. Now the standard error is 0.15. We'll check the previous version. The standard error is very small. It's very small, 0.056. Okay, standard error Smaller means it's more accurate, okay? The estimate is more accurate. And also it's true, it's quite accurate. It's quite close to the true value. Okay. Okay, so of course you may have your own version because we don't have the same data set. We have different data set. And you know what? This output is generated by using other seed. So it's different, okay? This estimate is 1.08. It's not same as ours, it's 1.02, okay? And also look at the standard errors, it's very large because in this case, I use 100 sample size. So standard error is so large, okay? Of course, we have Z value and probability. So for different seed, for different sample size, you will have different version of the estimate. But if you have the same seed, if you have the same sample size, you will have exactly the same result. Okay. So this is our output. Now that's for R. Okay, now we are going to use M plus to do the same data analysis. When the data is ready, it's the same data set, error M plus data, okay? So use the same data set. Now we use M plus to do the data analysis. Variable, in the observed variable, we only have one column, which is Y. Okay, so variable name is Y. Use variable, you're gonna use that column to do the data analysis. Just one variable, okay, Y. What is your model? Here, this is your model. T by Y at 1. Remember, we have M plus keywords. Remember what's the meaning of by? By. In the very beginning of M plus, okay, when we talk about M plus, we have on. On is short for is regress on. Okay, so we have regression relationship. But by using by, actually is short for is measured by. So this created a new variable called T. T is a new variable. By using by, we created a variable T because in the original data set, we just have Y variable. We don't have any T, okay? But by using by, we created a T. T is measured by Y fixed at 1. So this at sign means fixed. The coefficient from T to Y is fixed. It's fixed at 1. Based on CTT, the coefficient is fixed. We don't need to estimate that one. And also Y at 0.25, what does that mean? The variance of the residual Y is fixed at 0.25. And then T, what does that mean? We are going to estimate the variance of T. That is a model. We are going to estimate the variance of T. That is our goal. We only need to estimate one piece of one parameter, which is the variance of T. And this one is fixed. This one is fixed, just like in our code. The coefficient is fixed at 1. The variance of the residual Y is fixed at 0.25. We estimate T because we have one variable only. We cannot add more parameters. Yeah, so this is the explanation for M plus code. So T by Y means that T is a new variable is measured by the observed variable Y. Okay? T is a latent variable. By using the at sign, we fix a parameter. So let's go to the M plus. Okay. M plus. And the code is in ELC. So open after you download the code and open the file. Error M plus data.imp. Okay, so this is the first one. You can also have the second one. So that's it. So the error m plus data is just generated in R. We just generated the first step. I mean, maybe the budget. Okay, so here. So we're gonna highlight this part and run. So now, let me make it larger again. Okay, so in the very beginning part, just repeat our input code. And here, okay, here, actually the code is different as our slides code. So here I didn't put a T. I just fix this two. Because by default, the variance of T will be estimated. You can put a T and a semicolon, or you can just leave it flat. By default, the M plus will estimate for you. Okay. So we have the data information. Okay. Summary of the analysis, number of groups, one group, number of observations, 1,000, because we just generated 1,000 random variable Y. Number of dependent variable, 1, okay. Number of independent variable, 0. In our case, we only have one observed Y. We don't have independent variable because we are not going to run regression. There's no independent variable, no independent variable, just one dependent variable. And the continuous latent variable, look at this part, okay? Number of continuous latent variable, now it becomes 1. In the previous case, it's 0. In the previous regression or mediation or moderation, no latent variable, but here we do have T, latent variable, which is continuous, okay? We use by to create a T, latent variable. So the observed the dependent variable is Y, the continuous latent variable is T. We have two variables. The T is generated by the syntax of by, okay? And we have some other algorithm parameters. And this is our data file, error plus data, okay? We generated in R. And this is a data description part, okay? Skewness, kurtosis, mean, variance, variable, sample size, minimum, maximum, yeah, all the descriptive part. And model fit, okay, model fit. And again, okay, so here, the number of free parameters, why there's a 2? We said that there's only one parameter needed to be estimated. But remember that M plus consider mean and the covariance together. So there's a one part for mean, one part for the covariance. So in together we have 2. So the variance part is only 1. But by adding the mean part, we have 2 parameters. Okay. Likelihood value and the information criterion. Yeah. And the model result, okay, model result. Look at this result table. T by Y, it's fixed. T by Y, T measured by Y. So from T goes to Y, the estimate, the coefficient is fixed at 1. We don't need to estimate that. So the standard error and the ratio, it becomes, okay, this part becomes no. Actually, it's kind of like we don't need to estimate that because this is a fix. Okay, this is a fix. And yeah, this is the mean part of Y. We can ignore this part of variance of T. That's it. Okay, variance of T is estimated 1.012. If you run it up, it's just 1.02. In R, we have the actually, it's a little bit different. In R, it's a 1.02, 0 something. Let's go back to R. Okay, so what's the value? Yeah, here, this is the estimate of T, estimate of the variance of T in R. It's 1.0200, okay, 41. It's larger than 0.02, but in M plus, it's less than 1.02, okay. So it's different because, yeah, the different software. But the standard error also 0.057. What is R of? Yeah, if you run it up, the standard error is the same. And Z value here, the probability here. Yeah, Z value here, probability, yeah.
So when you were talking about bias, you meant like bias in the program?
Bias of the estimate. Bias of the estimate. So if you want to do the data generation, the simulation, because you know the true value, you can get the bias. But for real data, you don't know the true value. You don't need to get the bias because you don't know the truth because it's real data. Yeah, but for simulation, you know how these data are generated. So if you want to have the bias of the estimate, it's this case, this is estimate, okay. The estimate of the estimate, you can use this hat, okay. This is ME minus the true value of the variance of T. So it's 1.02041 minus 1. Okay, so this part is a bias. This is absolute bias, but if you want to use a relative bias, then this is the absolute bias. Absolute value of the bias divided by the true value. Okay, divided by the true value is 1. It's the same thing, okay, because the true value is 1 here. Yeah. So the bias, the smaller the bias means, okay, it's more close to the true value. So that means your model is really good because when you do the estimation, it's really close to the true one. That means the model is quite good. But for the real data analysis, unfortunately, we cannot do the test. We don't know the true value. So we don't need to report all of this. Yeah. Yeah. And for M plus, it's a little bit different. So the variance is here. Okay, this is the variance. This is the variance. So, but it's quite close. Okay, so if you do the comparison of this number, this model, same. And also this one is fixed because in the code we have already fixed the variance of the residual y. Okay, it's fixed. So we don't have any estimate. We don't have the T ratio. We don't have the probability. We just estimate this part. Of course, M plus also do the mean part. That is the intercept, the mean part of y. So we have another one. So in total, it said there are two parameters, three parameters. One for mean part, one for the variance part. When we talk about these slides, when we talk about these slides, the number of information, I mean the variance and the covariance component. Okay, mean part is not included. We have another formula for the mean part. So the number of information I just. Okay, so I think that's all for the M plus. So good. So let's go to the M plus. Of course, this data set, the slides here, is estimated by using other data set because the seeds is different. So you can see that it's different. It's different. Standard error also different. Sample size is 100. Okay, so this is a different result. The seed is different. And we can also use Amos. Okay, so if you want to use Amos, this is your model. T goes to Y, and it has been fixed. So in the Amos, you can just choose. Okay, click this row, and the right click. There are some options for you. You can just fix the weight. Okay, there's a coefficient weight. You can just put a 1 here. Then this coefficient is fixed at 1. And yeah, this is a variance of the t, okay, estimated by Amos. Of course, the value is different as ours because the city is different, the sample size is different. This one is fixed, okay? Same thing. If you want to fix the variance of E, so just right click, choose this one, right click, and there's a small box pops up, and it's gonna ask you, do you want to fix the variance of this part? Yes, and you're gonna change, you can change the value to 0.25. That's it. Okay. Also, this fix, and they will automatically run estimation for you. Got the estimate. And we also have the table, the output table from Amos. So there's the estimates. Okay, we have a lot of output, the estimates and scale. We have the variance of t. Okay, this one's fixed. This is a very estimate value. So the error t ratio. Okay, this is also fixed. Regression weight fixed. This is the variance part. Variance part. Any question for the first example? We just use R to generate the data, and we use the same data set. We analyze the model by using R, by using M+, and also by using Amos. So all the results are quite similar. Okay, so because the same data set, because the same model, although we have different software, the final results are quite similar. And that's our model, okay, in R. Okay, let's go to second example. Okay, now we have two observed variables. We have y1 and yt. I'm sorry, we have y1 and y2. Both of them are measured the same t. From the same t, we have two sets of observed variables. Same t, but due to different measure, different E1 and E2, we have two sets of y1 and y2. We have the same setting for E1 and E2. Again, let's check the number of information. In this case, how many observed variables? 2. Then what is the number of information? 3, exactly. Then we can estimate at most 3 parameters. In the first case, we can only estimate 1, but now it's much better. It's much better because we have 2 variables. We can estimate 3 parameters. Previously, we cannot estimate both sigma t square and sigma e square. Now it's possible, okay? And how many parameters? Okay, it depends on our session. If you want to estimate 3 parameters, one, the variance of the 2 score, one, the variance of E1, one, the variance of E2, it's possible. And then in that case, we have degrees freedom 0, okay? Okay, first step, again, it's simulation. We're gonna generate our data, almost the same code, okay? We're gonna set the seed. That seed is just randomly choose. I just chose today's date. So you can choose, okay, 1 or 2 or 3, whatever number. You can just choose that number to any number. But when you use the same seed, every time you run it, always have the same set of results. Okay, and T, R norm, random number from normal distribution, 1,000 sample size, mean of 0, 1 is the variance. And Y1 is T plus the residual. This is the E1, R norm, 1,000, 0 mean, 0.25 is wait a minute, we should use R square root, because that is a variance. Okay, so it's always confusing. So in our code, okay, this position should be used as standard error, not as a variance. Let me check the code. Did I use square root?
Yeah.
Okay, good. That's a square root. So here I should change it to square root. Yeah. So this is a standard error. Okay. Otherwise, it's different because you change the parameters in the generation. Okay, so we have, okay, So the code is good. Okay, square root of the variance. So this is the area of the variance. So y1, y2 is generated by combining T and E. And then we have two columns. I'm gonna combine these two columns together by using the C bind. This Y has two columns now. Y1 is the first column, Y2 is the second column. And you can also write, okay, table, save the current data into second data set. Okay, I call it 2, but you can just rename it. And starting from there to here, you just finish the data generation part. Actually, I should put. So this is the data analysis part. Starting from step seed to the right table, you finish the data generation part. You generated the two columns, two variables. And from here to here is your model part. Okay, this is a variance of your observed Y. Y has two columns, so the S2, the variance is a matrix. It's 2 by 2. It's a matrix because it's a two column. It's a 2 column matrix. And then what is your model here? From T to Y1, still I fix at 1 because based on CTT, it's fixed at 1. I don't need to estimate the coefficient here. It's fixed. T to Y2, same thing. I fix the coefficient at 1. I don't need to estimate this coefficient. So this is 1, this is 1. And here, I'm going to estimate the variance of T. Sigma T squared is estimated here. Here, I'm going to estimate this part because now it's possible for us to estimate more parameters. In addition to the variance of Q square, I also want to estimate the variance of the E1, the variance of E2. Okay, so this is part of the variance of E1. This is the variance of E2. Okay, but this is another code. This is try the other version, the constraint version. I want to try to make these two the same, S2, S2. But this is another exercise. Okay, so in the beginning, we can try this part. This is our model. Model 2, second covariance matrix. Okay, sample size 1000, and we can do the test on the model. See the variable. Okay, so we have R ready. So go to the second model, second example. Yeah, use the same seed and T. This is our T2 score. And the E1, E2, okay, E1 is generated here. And by adding T and E1 is our Y1. And the E2 is here. And by adding T and E2, we have Y2. Okay, so we can just write one together. So Y1, Y2 is ready. Combine these two columns, we have Y. So you can check the Y. Okay, you can check the Y. We have two columns. Okay. Yeah, this is the beginning part of Y. We have Y1, Y2. Y1 is the sum of T and E1. Y2 is the sum of same T and E2. T is the same. Okay, two scores the same. And we write table. Yeah, we're gonna save the table to your local folder. The name is yeah, and the variance of Y is calculated here. This is the variance of Y. Okay, it's 2 by 2. It's 2 by 2 matrix. This is the variance of Y1. This is the variance of Y2. This is covariance between Y1 and Y2. You can see the correlation is really high. Why? Why the correlation is really high for Y1 and Y2? Because
Measuring the same thing.
exactly. They are measuring the same thing. They measure the same T. Y1, Y2 is using the same T. So the correlation is really, really high. It's good. Okay. It's good. Okay. Then we have the specified model here, we just explain this small as three parameters. And then we have SEM and random. Now we have three parameters. Degrees freedom 0. We use all the information. This is sigma t, sigma square for t. This is sigma square for E1. This is sigma square for E2. You can see that sigma t squares, again, it's close to 1. But it's not 1 because this is not the population 1. This is not the true value. It's an estimated value based on our generated data. Okay, this is estimated sigma, sigma square for t. And S1, the true value actually is 0.25, but now we have 0.29. The bias is 0.04. And this one, the true value is 0.25. The estimated one is 2.21. Again, the variance, the bias is 0.24. It's not the same true value, but it's quite close to the true value. Okay. And the standard errors are small, okay? And the z-value probabilities. Okay. Any question? Any question for this part? And again, if you change your seed, or if you just ignore that seed, you will have different set of estimates because the data is totally different. By using the same seed, all of these results are the same as this one because you use the same data set. Okay, yeah. Okay, then we can also use M plus. Okay. M plus, go to GLC, download the M plus 2. Okay. M plus. Okay, here I have some comments. So this is means that we can just change the code a little bit. Yeah, so, oh, I didn't talk about M plus. Okay, so let's go to the slides. So this is out. Again, the output here is different because I use different set of data. So you can see that it's different. Here it's quite close, okay? But it's different. It's different as ours. So we have the same areas. If we use M plus, this is our model. Okay, model here, Y1, Y2 based on the same T. So Y1, Y2 is our observed variables in that data set. We're gonna use both of them. The model, this is our model. What does that mean? T by I1 to Y2. T is a new variable. It's not included in the data set. Y1, Y2 are the two variables, but now I'm gonna create a new variable called T, which is latent. T is measured by these two variables. T is measured by these two variables, observed variables. But the coefficient is fixed at 1. So here we have two variables. You can use a hyphen to connect them. If you have a many, for example, the T is measured 10 times from Y1 to Y10. So you can just say, okay, Y1 hyphen Y10, it's the same, okay? All the coefficients has been fixed at 1, fixed at 1. And here, what does that mean? Y1 to Y2. I'm gonna estimate the variance of the residual Y1. Also, I'm gonna estimate the variance of residual Y2. T, okay, I'm gonna estimate the variance of T. 3 parameters, these are 3 parameters, okay? And if we use this code, that means, okay, we're gonna fix the variance of Y1, Y2, the same one as one. We can try it next time. Yeah, so this is our code. This is our code. So if you go to M plus, yeah, so this is the original code. Actually, I should put a comment here. Yeah, this is you can just change the code a little bit to have a new model. So suppose this is our model. I'm gonna save it. This is our code, input code. number of dependent variables in this case, 2, y2, okay? Number of latent variables 1, which is t. So two dependent variables here, 1, 2. T is generated. Algorithm, okay, statistics and modify degrees freedom. Where's the degrees freedom? Model result, okay, here, model result. T by y1, y2, fixed at 1. We don't need to do the estimation. This is the mean part and the variance part, okay, variance part. And there's a residual variance. So you can do the comparison for the sigma t squared. It's 0.972. Yeah, okay, here it's 0.973 if you round it up. So again, they are not the exact same, but they are quite close to each other. So this is the variance of t. This is the variance of the E1, the first measurement, okay? 0.297. Yeah, it's the same, 0.297. This is a 0.2119. This is 212, yeah, it's the same, okay? Same errors. Same errors. Yeah, same errors here. Errors here. Good, okay, that's a result from M plus. Of course, you can ignore this part. This part is from another data set. So of course, the variance and the residual variance are different. If you want to put a constraint, if you want to make sure, no, it's not here. The variance of two, the variance of here, the variance of two residual parts is the same. We can assume, okay, the variance of E1 and the variance of E2 is the same. Then you're gonna put this constraint, okay? Y1 and Y2, the variance part is the same name, same parameter name. Okay? Then you have the same result. So if you go to N plus, you're gonna change the code a little bit. Yeah, by putting this one and put this comment. Put this one. So this is our new model. In this case, what's the degrees freedom? If I put this constraint, what is the degrees freedom for this model? Degrees freedom. How many parameters I'm gonna estimate in this case? One, which one? This is a new model. Please ignore this part. This is a comment. Okay, this is comment. You're gonna ignore this one and look at this part. How many parameters we are going to estimate?
3.
Which 3?
T, Y1, and Y2.
T,
Y1.
you mean variance or just T? It's different. T is a random variable. You want to estimate the variance of random variable or just T? It's different. It's totally different.
The variance.
Yes. Variance of what? Variance of which variable? You said 3. So 3. Which 3 parameters?
The variance of Y1.
Residual Y1. Variance of Y1 is observed.
Okay.
Residual Y1, which is E1.
Mm-hmm.
Okay, and what's the second one?
The residual of Y2.
Okay, and then which is the third one?
The variance of T.
Yes, but here I put a constraint. Not quite, okay.
You did it.
Yeah, you did it.
Almost. So what's the meaning of this constraint?
You constrain the variance.
The variance of the residual y1 and the variance of residual y2 is the same. This is the meaning of this parameter. This is a parenthesis. Remember, after we put a parenthesis, put the same number, we constrain these two parameters are the same.
Okay.
So we assume the variance of E1 and the variance of E2 is the same.
Mhm.
Then,
Oh, yeah.
then how many parameters in this case? How many parameters we are going to estimate in this case?
2.
Yeah, because we assume variance E1 and variance E2 is the same. We don't need to estimate the 2. So in total, we have 3 number of parameters. We have in total, we have 3 number of information. We have 2 parameters. What's the degrees freedom in this case? What is the degrees freedom in this case? Anyone?
1.
Yes, it's 1. Okay, let's try to run this code, okay? Okay, so this is the code. And we have, let's look at here. Let's look at the result, okay? This is fixed, we don't need to estimate it. Intercept, we can ignore this, but this is the mean part. The variance of t-score here. Now, let's look at the residual variance, residual y1 and y2. They are exactly the same. They are exactly the same, exactly the same, exactly the same. Because we put the constraint to make them equal, okay? So we have variance of t estimated here. We have variance of E1 and E2. The degrees freedom here is 4, but why is 4? Because we have 2 for the variance part, 2 for the mean part. We also have 2 y1, y2, the mean part for each of them. In total, it's 4. Okay. And plus consider mean and variance together. Okay, so we have so if we put them constrained, they are exactly the same. And if we want to use AMOS, then that's a path diagram. We're gonna create that path diagram in the right panel of the AMOS, then we're gonna estimate the variance of E1, variance of E2, variance of t-score. Okay, that's it. That's it. And we have the table. Okay. So variance of t here, variance of E1, variance of E2. Okay. If we put constraint, they're the same. Okay. There's a box. Okay. You can put this the same. And all of these are the same. Again, please ignore this detailed number because it's different data set. So the final estimate is different. Okay, that's for today's lab. So so we have already done. So for the R part, if you try to make them the same, you're gonna have the other code. Okay, so you can try to modify it a little bit.
Oh, I can't make this R package short.
Yeah, you can make it S2. Okay, if you make it S2, then you have model 3. Model 3. Model 3. Sorry. When I install it. Then try to that's it. This is our result. In this case, we only have 2 parameters. So these 2 are the same, E1, E2. This is the T part. Okay. Because freedom in this case in R is 1. Okay. Good. Okay. That's for today's lab. Any question? Any question? So here we introduced the data generation. Okay, so how to generate our data to do the simulation study. This is your design. Okay, you assume the data is just like generated like this. Question? Question?
I have to think long and hard about my project. I know I will.
You gonna do the real data analysis. So just forget the data generation part. That's for simulation.
Oh.
Yeah. So you have your real data. You're gonna describe your data. what is the basic statistics
Oh, yeah.
for each
yeah,
variable.
right.
And
I thought I
then
installed something.
you're gonna run the data analysis,
Mhm.
and then you provide the final result. That's it. You don't need to check the bias because you don't know the true value.
Oh, the only thing I remember about is the equation. 'Cause I showed you. I
Okay.
have multiple mediators that I want to use.
Okay, so you have two versions. Okay, you have the previous version, you have the second version. You're gonna use the second version, right?
Yes, but
Okay,
the direct paths are not significant, if that makes sense.
oh, that's okay. Okay, so if the results are not significant, it's totally fine.
Okay.
Because the goal of the final project is push you to try, I want you to do the exercise. It's not for the real, of course, if you want to publish that, we can
Right.
just modify it. We have other continued work. But for course project, it's totally fine.
Oh.
It's
okay.
totally fine. If it's not significant, just report it's not significant. Yeah, it's not big deal. Yeah,
Because my larger data set is significant, but
that's okay. That's fine. Yeah, that's fine. Yeah,
just making sure.
okay.
Copy and paste
Okay,
it.
any other question?
Like second.
Okay, then we can just stop here. So that's
Yeah,
our, basically that's our SEM1. And next class, we're gonna have a summary and also questions. Okay, homework, yeah. Please make sure you have already submitted all your homework and also revise the version of your homework, okay? Yeah. I think that's it. That's all. Yeah.
Thank you.
Well, thank you.
Are you able to run this on like your computer? Run SEM?
Yeah, I can run it. Yeah.